I was staring at a dashboard the other day, just a standard microservices setup, nothing fancy.
Mhm.
And I saw a connection refused error, just those two words, and it really hit me. I
Right.
spend my entire professional life writing code in Python or JavaScript, relying on these high-level APIs to talk to each other. But when that connection breaks, it just feels like the lights go out in the building. I have no idea what's actually happening down there in the dark.
That is such a common feeling. I mean, we live in the penthouse of software development rest, GraphQL, gRPC. It's nice up there.
Yeah, great views.
Great views, comfortable furniture,
Mm-hmm.
but the plumbing, the electricity, that's all happening in the basement.
And that is exactly where we are going today. We are going fully subterranean. We're doing a deep dive into the hidden infrastructure of the network layer.
We are peeling back the layers of the operating system to see how data actually moves. Because, for most developers, the network is just this black box. You put a request in
And you get a response out.
and you get a response out. It's magic.
But our mission today is to go from magic to mechanics. We've got a stack of research here based on Chapter 3 of Learning API Styles, and we're going to trace the journey of a single request.
A single request.
We're talking about everything from raw sockets and TCP handshakes all the way to the modern security of TLS 1.3.
It's basically the biography of a data packet, how it leaves your code, survives the chaos of the internet, and arrives safely at the other end.
So let's start the very, very beginning.
Yeah.
The moment my code decides to send some data, in my head, I kind of imagine my code just reaching out to the network card and pushing bits onto the wire.
Right.
But the source material makes it really clear that is absolutely not what happens.
No, and honestly, you really wouldn't want it to be. If every single application could touch the hardware directly, your computer would crash every 5 minutes. It would just be anarchy.
Right. Everyone fighting for the same cable.
Exactly. So computing has this really strict division of labor. You have user space, which is where your app lives, where your variables are, where your browser is running, and then you have kernel space.
The OS's VIP section?
That's the OS's VIP section. The kernel controls all the hardware, the memory, the CPU, and importantly, the network card.
So I'm in user space. I want to send a message. I can't cross that line myself.
Nope. You have to ask permission, and that is where the socket API comes in. It's the gateway.
The gateway.
When you write a line of code to open a connection, you're essentially making a system call a syscall. You're knocking on the kernel's door and saying, hey, I need a communication endpoint.
And that endpoint is the socket.
Correct. A socket is just an abstraction. It's a file descriptor that the OS gives you. It says, okay, write your data to this handle, and I will take care of all the heavy lifting.
And by heavy lifting, you mean the buffering, the electrical signal.
All of it. The timing, all the stuff you do not want to worry about.
Now, whenever we cross that boundary from user space to kernel space, the slides mention something called context switching. That sounds expensive.
It is expensive. The CPU has to literally stop running your code, save the state of your application, switch modes to run the kernel code, do the network stuff, and then switch all the way back.
Wow.
That takes time. It's why high-performance networking is so hard. You want to minimize those switches.
Okay, so we've got our socket, but the sources break this down into a life cycle, and they really distinguish between a server and a client. And reading the server setup, it sounds kind of exhausting. It's not just open.
It is a process. Think of it like opening a retail store. If you're the server, first you call socket to get that file descriptor.
Right.
Then you call bind.
And bind is claiming the address, isn't it? It's saying, this port is mine.
Yes. You are telling the kernel, any traffic that comes to this IP address on this specific port, say port 80, it belongs to me.
Yeah.
You're signing the lease on that digital location.
Okay, so I've signed the lease, but I'm not open for business yet.
Not yet. You have to call, listen. This tells the OS to start a queue. You're basically flipping the sign to open, but you're mostly just telling the OS, I'm ready to accept customers. Please line them up outside for me.
And then the final step, which I found really interesting, is accept.
Accept is where all the action happens. And here's the key. This is usually a blocking call.
Blocking, so my code just hangs.
It hangs. It effectively pauses. It sleeps. It waits. And when a client finally connects, accept, wakes up.
So it just sits there until a client knocks on the door.
Exactly. And when it wakes up, it returns a new socket, specifically for that one connection.
Oh, wait a minute. So the original socket, the one we bound to the port, that one stays listening.
Yes. The listening socket stays open to welcome new people. The connected socket is created just for that one specific conversation. That's how a server can handle thousands of users at once.
That's a crucial distinction. I think I've missed that before. Now, the client side is much easier, right?
Oh, much easier. Ideally, they just call socket and connect. If connect succeeds, we're in the game.
And then we're in the loop.
We enter a loop of send and send and receive,
Until someone calls close.
which hopefully is a graceful shutdown.
Hmm.
If the app crashes, the OS has to clean up that whole mess, sending reset packets to everyone to say, the party is over, go home.
Okay, so that's the interface. That's how we talk to the OS. But once the OS takes my data, it has to format it for the journey. And this brings us to the famous or maybe infamous battle between the OSI model and TCP/IP.
The eternal battle, yes.
I feel like everyone learns the OSI model in university, the 7 layers: physical, data link, network, transport, session, presentation, application. It's very elegant. It looks great on a poster.
It is beautiful. It is also largely theoretical. It was designed by a committee before the internet, really took off.
So in the real world, we use TCP/IP.
We do. The TCP/IP suite simplifies things down to 4 practical layers: link, internet, transport, and application. And honestly, for a developer debugging a production issue, this is the model that actually matters. You don't really need to worry about the session layer, because in TCP/IP, that's just part of your application.
The source material uses this Matryoshka doll analogy for how data moves through these layers. I thought this was great because encapsulation is such a fancy word, but the concept is actually pretty simple.
It's just wrapping paper. Let's say your application wants to send a JSON object.
Yeah.
Hello world. That's the application layer data. To the OS, that's just a payload.
Okay.
The OS takes that payload and passes it to the transport layer.
Yeah.
Let's say TCP. TCP doesn't care what the data is. It just prepends a TCP header. Now, that whole bundle is called a segment.
So the data just got bigger.
Yes,
Right.
we added overhead. Now, TCP passes that segment down to the internet layer IP. IP adds its own header, the IP header, which contains the source and destination addresses. Now it's a packet.
Even bigger.
And finally, it goes to the link layer, your Ethernet or your Wi-Fi. It gets wrapped in a frame header and a footer. Now it's a frame ready to be turned into light or electricity.
It's literally dolls inside of dolls. And when it hits the other computer, it's all in reverse.
Exactly. Decapsulation. The other OS strips the frame, looks at the packet, strips the packet, looks at the segment, strips the segment, and just hands the raw JSON up to the application.
This really highlights why we worry so much about packet sizes. Every time you send data, you're paying this tax of headers on every single layer.
Precisely. If you send 1 byte of data, you're still sending 60 or more bytes of headers. It's wildly inefficient. That's why we buffer data to send more payload for the same amount of tax.
Now, inside those headers, we have the address information. And the notes here distinguish between IP addresses and MAC addresses using an office building analogy. I want to dig into this because I think a lot of devs treat them as interchangeable, but they really, really aren't.
No, they solve completely different problems. The IP address, that's layer 3, is about the network. In the analogy, the IP address is the floor number of a massive office building. It gets you to the right general area.
And routers use this, right?
Right. The router looks at the IP and says, oh, this goes to the 192.168 network. That's the 4th floor. It doesn't know which specific computer you want yet. It just knows the neighborhood.
So once I'm on the 4th floor, I need to find the specific desk.
That is the AM address, layer 2. The media access control address is physically burned into the hardware of the network card. It's the permanent ID of that specific device.
So the IP gets the package to the building and the floor. The MSC gets it to the specific person at their desk.
Exactly. Switches use the MSC address to make that final handoff. You can change your IP address, you can move desks, but your MSC address stays with the hardware.
Okay, so we found the machine, we've knocked on the door, but we can't just start shouting data at it. We need to make sure they're listening. This is where the TCP 3-way handshake comes in.
The conversation starts.
So why do we even need this? I mean, UDP just sends data, right? Why is TCP so formal about everything?
Because the internet is fundamentally unreliable. It's a messy place. Packets get lost. They arrive out of order. TCP's whole job is to guarantee a reliable state. It ensures both sides are ready before we waste time sending any real data.
Okay, so walk us through the steps. It's a dance.
It's a 3-step dance. Step 1, the client sends a SYN packet. That stands for synchronize.
Okay.
Basically say, I want to open a connection, and here's my starting sequence number so you can track my messages.
And the sequence numbers are how we put things back in order if they get scrambled.
Exactly, because they will get scrambled.
So the server receives the SYN.
The server replies with the SYN ACK. synchronize and acknowledge, saying,
Mhm.
I see your sequence number, here's my sequence number, and yes, I am listening.
And then the client finishes it off.
With an ACK, I acknowledge your sequence number. At that point, the connection is established.
It seems like a lot of back and forth just to say hello.
It is, and that latency adds up. That's a full round trip before a single byte of your application data is sent. But it's the price we pay for reliability. If that handshake fails, your application gets connection refused immediately, rather than sending data into a black hole and just wondering why no one ever answered.
Speaking of seeing this in action, reading about it is one thing, but the source material is really big on getting hands-on. They suggest building a TCP echo service.
I love this exercise. It is the hello world of networking. You write a server that simply accepts a connection, reads whatever text comes in,
Then sends it right back.
and sends it right back. No database, no business logic,
Nothing.
none. It forces you to write that socket, bind, listen, accept loop we talked about.
Yeah.
You see exactly when data arrives. You realize that hello might arrive in two separate chunks or combined with the next message.
Yeah.
You have to handle that raw stream yourself.
And to debug that, the deep dive lists some tools of the trade. Some of these I know, some are new to me. Netcat seems to be the big favorite.
Netcat, NC, is the Swiss Army knife. It lets you read and write data across network connections manually. You can literally type ncgoogle.com/80. Hit enter, type GET HTTP 1.0, and you'll see the raw HTML come right back at you.
That's so cool. It just strips away the browser entirely.
It shows you that at its core, the web is just text. There's no magic.
Then there's Wireshark. I've opened Wireshark before, and honestly, it looks like the Matrix code. It's just overwhelming.
It is the X-ray machine, captures everything that goes across the wire. But once you understand encapsulation, Wireshark makes sense. You can click on a packet and see the bottom pane divide into tabs, Ethernet, IP, TCP, and payload. You can verify all the headers we just talked about.
And if you're using standard TCP, you can see the payload too.
You can. If you send a password over plain HTTP, Wireshark shows it in plain text for anyone to see.
Which brings us to the final and probably the most critical part of this deep dive, the shield, security. Because we can't have our data traveling naked across the internet.
No. Any router between you and the server, and there could be 15 or 20 hops, can inspect that traffic. We need TLS, transport layer security.
Most people just know this as the little padlock icon in the browser. But under the hood, it's doing three very specific things: confidentiality, integrity, and authenticity.
Right. Confidentiality is encryption, so nobody can read it. Integrity means nobody changed it. If I send pay $10, a hacker can't change it to pay $100. And authenticity, this is a tricky one, means I know I'm actually talking to my bank and not a hacker pretending to be my bank.
The way TLS achieves this is described as a coordinated dance using three types of math. This part always trips me up. Why do we need three different types? Can't we just use one really good key?
We can't because of performance, really.
Okay.
First, you have asymmetric cryptography. That's public and private keys. This is amazing because you can share a public key with anyone, and they can encrypt a message that only you can read with your private key.
Okay, so why don't we just use that for the whole conversation?
Because it's incredibly slow.
Yeah.
It just burns CPU cycles. So we only use it for one thing, the key exchange. We use that slow, secure math just long enough to agree on a shared secret password.
And once we have that shared password...
We switch to symmetric cryptography, like AES. This is the second pillar. Symmetric encryption uses the same key to lock and unlock, and it is incredibly fast. This is what protects the actual movie you're streaming or the file you're downloading.
Okay, so that's two. What's the third pillar?
Hashing. This is all about integrity. We run the data through a math function to get a unique fingerprint. If even one single bit changes in transit, the fingerprint changes, and the receiver knows the packet has been tampered with.
So, asymmetric to share the key, symmetric to lock the data, and hashing to verify it. That's the tech. But the source makes a really profound point here. The math isn't enough. I can encrypt a message to you perfectly, but how do I know you are actually you?
Exactly. I could be a man in the middle. I could intercept your request to Google, pretend to be Google, and give you my public key. You'd encrypt your password, send it to me, I'd unlock it, read it, and then forward your request to the real Google. You would never know.
That is terrifying. So how do we stop that?
We need a chain of trust. We need a trusted third party that we both believe in to vouch for our identities. And this is the Certificate Authority, or CA.
The trust anchor.
Yes. Companies like DigiCert or Let's Encrypt. What they do is they digitally sign the server certificate.
So when my browser connects to a website, it's not just looking at the math. It's looking for that signature.
It checks the signature against a list of trusted CAs that are pre-installed in your browser or your operating system.
Hmm.
It's effectively saying, look, I don't know the server personally, but I know the guy who vouched for him, so I'll trust him.
It really, really relies on those CAs being rock solid.
It does. If a major CA gets compromised, the whole system gets very shaky.
Now, all of this setup happens in the handshake. And the deep dive mentions that TLS 1.3, the modern standard, has significantly changed how this works.
Oh, it's so much faster.
Mm.
In the old days, you had the TCP handshake, then a multi-step TLS handshake. It took forever. TLS 1.3 tries to do as much as possible in the very first message.
In the client hello.
Right. The client is eager. It sends the client hello, but it also guesses which encryption algorithms the server might want, and it sends its key shares, public key part, right away. It doesn't even wait to be asked.
So we save an entire round trip.
We call it 1 RTT, 1 round trip time. By the time the server responds with its server hello and its certificate, the keys are already derived. The handshake is effectively done.
And one detail I found fascinating, TLS 1.3 encrypts the handshake itself much earlier than the older versions did.
Yes. In older versions, the certificate, which contains the site name you were visiting, was sent in clear text. An eavesdropper could see which sites you were visiting, even if they couldn't read the content. TLS 1.3 hides much more of that metadata.
So if we go back to our X-ray machine to Wireshark and we look at a TLS 1.3 connection, what do we actually see?
Phase 1, the handshake, you still see some visible metadata. You see client hello, you see TLS 1.3, but then almost immediately, it just turns to static.
Encrypted garbage.
Just random alphanumeric
Mhm.
characters. It's hypertext, the payload, the application headers, the path. It's all completely opaque. That is the shield in action.
It is just incredible to think that every single time I click a link, all of this happens. The OS creates a socket, ARP finds the MAC address, TCP shakes hands, TLS negotiates keys, certificates are validated.
And it all happens in milliseconds.
It is the most complex machine humanity has ever built, and we just expect it to work.
And usually it does. But understanding these layers, from the socket all the way to the shield, that is the difference between a coder and a true engineer. When things break, you know where to look.
You aren't afraid of the dark anymore.
Exactly.
Before we wrap up, I want to leave our listeners with a provocative thought, something that really stuck with me regarding that chain of trust.
Go for it.
We place this implicit faith in these certificate authorities. There are hundreds of them trusted by your computer's root store. If just one of them goes rogue or gets hacked and issues a fake certificate for google.com or yourbank.com, the math doesn't save you. Your browser would trust it.
That is the existential risk of the internet. The cryptography is sound, but the trust model is human. And humans are hackable.
A little paranoia to keep you sharp.
It's always healthy.
For everyone listening, don't just take our word for it. Open a terminal, run curl-v google.com, look at the handshake, watch the lines of text fly by, and try to spot the layers we talked about today.
See the mechanics behind the magic.
Thanks for diving deep with us on the hidden infrastructure. We'll catch you on the next one.